All right. So, welcome everyone to another edition of the Stellar Seminars. Today's speaker is Professor Mariya Zheleva, Professor of Computer Science at the University of Albany, SUNY, in the US. She graduated with her PhD in Computer Science from the University of California, Santa Barbara in 2014. She holds a Master of Engineering and a Bachelor of Engineering in Radio Communications from the Technical University of Sofia in Bulgaria. She leads the UBNet Lab, which conducts research at the intersection of wireless communications and information and communication technology for development. Mariya is the recipient of the NSF Career Award, the Dynamic Spectrum Alliance 2019 Award for the University Research on New Opportunities for Dynamic Spectrum Access, and the University at Albany 2019 President's Award for Exemplary Public Engagement. She's the co-lead for the NSF-supported National Radio Dynamic Zones Partnership and Workshop Series, and the founding member of Spectrum X. And the title of the talk today is Radio Dynamic Zones, Motivations, Challenges, and Opportunities to Catalyze Spectrum Coexistence. So, Mariya, take it away.
Hi, everyone. I hope you can hear me okay. So to be able to see my slides where I speak, I'm going to minimize the window with your faces. So if anyone has a question, I don't think we should keep those until the end. Just feel free to unmute yourself and jump in, or maybe comment. You're gonna moderate questions as you see fit. So yeah, I was telling everyone who joined earlier, I'm a computer science and computer engineer type of person. I generally dabble in active communications, and I've been fascinated with just originally the need for more spectrum for mobile broadband, and that's sort of where my foray into coexistence started. My research is broadly in spectrum measurement and spectrum analytics. So how do you make sense of radioactivity that you're seeing within a spectrum trace? And I do have another live that deals with connecting rural areas, and that I'm not going to actually talk about a whole lot within this talk. But through this path of spectrum analytics and spectrum measurements leading to coexistence, I've stumbled upon two initiatives that have helped me kind of broaden my view of who else is using the spectrum and what might it mean to share more broadly. So beyond mobile broadband, other spectrum stakeholders such as radio astronomy, such as remote earth sensing, that are there and actively using the spectrum, but not necessarily by transmitting in it. And so this has created a whole sort of new perspective for me on spectrum coexistence that I've been able to explore through two initiatives. So one is what Carmen mentioned, the National Dynamic Radio Zones Initiative. And I'll talk about this just a little bit in the next slide. And the other one is through my engagement with Spectrum X, which is a National Science Foundation Spectrum Innovation Center that brings together academics from across the United States, across different disciplines, so both scientific users of the spectrum as well as what's considered active commercial users of the spectrum, to just ponder upon the future of spectrum needs and how do we enable coexistence through both technological academic innovation as well as through informing policy. So I did mention about the National Radio Dynamic Zones Partnership. So essentially, this is a think tank, again, supported by the National Science Foundation. We've been operating since 2020, so about 4 years now, with the idea of try and think about first the need and capabilities of different stakeholders, and then think about how might we design a wide area testbed that would support coexistence in a controlled manner, so that we can convince ourselves that we can actually coexist without harming each other, and then thinking in how this translates into more global policy and commercial technologies as well. So folks I've been working with continually are Chris Anderson, who used to be in academia, and then he escaped to be with the federal government. So he's now with the National Telecommunications and Information Administration at the United States. So this is the arm of the government that manages spectrum for non-commercial use. Chris Dupree is the Deputy Spectrum Manager for the National Radio Astronomy Observatory, and he's been representing and sort of bringing in the radio astronomy community. Mustafa Akso and Joel Johnson are prominent researchers in remote Earth sensing. So they've been bringing a really important perspective on how the spectrum is used for weather prediction, climate science, agriculture, and so on and so forth. And Kevin Gifford has also, dabbled with Coexistence for quite some time, hailing from, like myself, from the active community. So majority of what I'm going to tell you about today is essentially thoughts that have been produced as a result of all of these people's efforts and our ability to engage over 150 researchers throughout the discipline. So it's not my view. I'm going to try and channel these 4 years worth of discussion around coexistence and how do we build a testbed to support coexistence. In terms of what I want to tell you today, so I want to start with a background of where we as a community feel that spectrum congestion is coming from and the types of conflicts that this congestion is resulting in. Then I'm going to talk about a vision for this national radio dynamic zone as a wide area testbed that can potentially help facilitate coexistence research in trustworthy and controlled environment. I'm going to talk about some of the grand challenges in realizing this testbed. And I'm going to wrap up by talking about some of the spectrum awareness research that we do in our lab as much time allows. Which, by the way, how much time do I have? I think we talked about, about 45 minutes. Okay.
Yeah.
All right. And just as a disclaimer, there's a lot of agencies involved here that I mentioned, but the thoughts and opinions in this presentation are really mine and of my collaborators alone, and they do not necessarily reflect the views of their respective employment agencies. So with that, the problem of spectrum congestion. I feel like I cannot be talking about spectrum without showing this convoluted and pretty graph to the right-hand side of the slide. So this is the National Telecommunication and Information Administration's frequency allocation chart, or in other words, what the government of the United States thinks that different parts of the spectrum between 0 kilohertz and 300 gigahertz should be allocated for, or are allocated for. So this view sort of gives the impression that spectrum is carefully managed and allocated and assigned. But what it really only shows is what's the thought process in allocating different bands to different users. And this was conceived tens of years ago, right, mid of last century. And it hasn't been evolved a whole lot as our spectrum ecosystem has changed over the past 30 years. And so really what it doesn't show at all is how the different bands that were allocated to technologies were actually used as time progressed and as our technologies evolved. So the question then is, if spectrum is so carefully managed, why are we having issues in the first place? And really what it boils down to is that what this allocation of spectrum has resulted in is really siloed way of thinking about spectrum that has really led to different constituencies that make use of the radio spectrum not talking to one another at all and being awfully protective about the spectrum that they use for various and oftentimes very good reasons. At the same time, we're confronted with this. So what I'm showing on the right-hand side is the study that we recently published that on one hand, sort of surveys where spectrum conflict is coming from, and then looks to conceptualize this national radio dynamic zone. But what we see here on top is, horizontally in a wide frequency range up to 50 gigahertz, and vertically over the years from 1990 and with a projection into the 2030, what were the spectrum needs and allocations for consumer broadband technology? So that includes cellular, Wi-Fi, and low Earth orbit satellite constellations. That's in purple, remote sensing in green, and radio astronomy in blue. And so I should say that darker colors indicate allocations, whereas lighter colors indicate capabilities. So we can see that over time here, Whereas earlier on, technologies were fairly narrow band and were broadly able to live within their own pieces of spectrum without interfering with one another too much. Now, as time progresses, all the stakeholders are becoming more and more capable in terms of their instruments to observe or actively utilize the spectrum. And consumer broadband is getting a bunch of allocations that increasingly abut or overlap with spectrum capabilities for other stakeholders across the remote sensing and radio astronomy communities. The bottom graph just shows over time how has the instantaneous bandwidth capabilities evolved of those different stakeholders. And we see, again, that everybody is growing in how much bandwidth they can use instantaneously and how much they can observe instantaneously. And this problem of, basically different stakeholders trying to utilize the same pieces of spectrum is only going to get worse as we continue as individual communities to grow in our capabilities and needs. So to hone in more on the individual stakeholders' capabilities, this was a result out of a publication by Andy Clegg that surveyed what the Green Bank telescope's observations were focused on, more specifically in which bands they were measuring. And so across if you consider bands across those that are exclusively allocated and others that are not, radio astronomers at the Green Bank Observatory really only spend 15% of their observing time in allocated bands, and their instruments have expanded in capabilities to be able to do much more comprehensive science in bands outside of those allocations. So they often follow those phenomena within different bands. In terms of what 6G and next generation mobile broadband is going to look like, it's essentially a lot of heavy utilization. The moment a mobile broadband user steps onto a piece of spectrum, that spectrum is going to be completely and fully utilized by the amount of demand that those stakeholders create onto spectrum. And so currently, we have only one way to kind of evaluate spectrum use and evolve policy, by looking at whether spectrum is idle or occupied, and then if it's perceived idle, allocating it or reallocating it to mobile broadband users. However, what we need to realize and start accounting for in measuring for informing policies, that the fact that you cannot measure certain spectrum activity, or that you're not, because there is none, actively, or that because you're not sensitive enough to measure that activity, it does not mean that the spectrum is actually not in use. And so effectively, data-driven policy should really encompass the various sensitivity levels and the passive active capabilities of stakeholders that employ various spectrum chunks before those spectrums are open for the use of commercial broadband technologies, whose spectrum utilization looks like this over time, right? Quite heavy and continuous. In terms of kind of coming together as across different communities, there has been different communities to operate on the same spectrum. It's not the first time we're trying this, right? So there has been a couple of attempts in the past to convince each other as communities that if one active technology operates close to a passive technologies band, that they're not going to be affected. And that really has resulted in a bunch of broken promises. So a couple of examples that keep coming up in our discussions from the radio astronomy community are when GLONASS was launched on a band that was fairly close to a radio astronomy protected band. Through theoretical analysis, it was deemed that the GLONASS emissions will not affect the radio astronomy protected band. However, this radio astronomy protected band that is here illustrated or highlighted in yellow, effectively the emissions from GLONASS did not fall below the harm threshold. And that was one instance where it was irreversible. The harm that was done was irreversible, because we're talking about, an orbit based navigation system that is now leaking perpetually within what was originally protected bands. Other examples, stem from the Iridium constellation being launched and, leaking into the NGVLA, as is the example here, at the onset of the launch and continuing unremedied as time progressed 10 years down the line. Earth sciences or remote sensing of the Earth are not protected either. And those two are critical sciences. So if you've ever tried to look at the weather forecast in order to decide what to wear, or whether to evacuate as a result of an impending hurricane, that's an outcome of what Earth sensing does in order to predict weather and to predict the climate. They observe Earth on various radio frequency bands in order to capture Earth's natural emissions. And those observations are broadly, satellite borne. So they're looking from space onto Earth in order to understand various properties of the soil and of the oceans in order to predict, various climatological aspects. And so if you think about remote sensing coexistence with mobile broadband, what is more important? Being able to download cute cat images or having accurate weather forecasts, being able to survey clients, or climate change, support smart agriculture, and maintain accurate climatology. And those are kind of questions that you cannot easily put a price tag on, or at least not as easy as what's the price of downloading a cute cat image, but are increasingly important to be able to put in an apples to apples comparison in order to continue moving the needle in efficient coexistence and avoid situations such as this one, where in certain bands of interest, the spectrum is so polluted that no meaningful sensing can be performed for those sciences. So far in allowing coexistence, we've seen a couple of progresses with dynamic spectrum access and dynamic spectrum sharing that broadly make use of exclusion zones in order to ensure that the various stakeholders do not interfere with one another. One prominent example that is, again, United States centric is what we refer here to as the CBRS, or Citizen Broadband Radio Service. So that is a spectrum sharing framework that effectively allows mobile broadband operation in bands that are traditionally used by naval radar ships. So effectively, naval radar is a spectrum user that occurs along the coasts. That's where they guard and that's where they need their instruments. Traditionally, the spectrum was allocated throughout the entirety of continental US, whether they were along a coastal line or not. And at some point, we figured out that maybe we can reallocate part of this for mobile broadband, as long as we're able to efficiently protect and ensure interference-free operation of those naval radars where they need to use the spectrum. And this was done through exclusion zones. So effectively, we're going to create these exclusion zones. We're going to perform spectrum sensing to sense the radars in order to make sure that we can detect the radars. We're not going to allow much transmission from mobile broadband in those bands, in those areas. And this resulted in high inefficiencies in spatially how much the spectrum could be reused, to where about 60% of the US population effectively fall on exclusion zones. And that made it particularly uncompelling to the mobile providers to make use of that spectrum. And things could have been done more efficiently, and are now. Another example with radio astronomy observatories sharing with Starlink type of stakeholders, so low Earth orbit satellites. The thought process now is that anytime a Starlink satellite passes over the zone of view of a radio astronomy instrument, they're going to shut down as to not interfere with the astronomy instrument and then resume operation. But if you simulate what the view of one of the the biggest radio astronomy single dish instrument, the Green Bank telescope, looks like, it effectively covers the majority of continental US. So if you're going to make this into an exclusion zone for low Earth orbit satellites to operate, then again, we're running into quite substantial inefficiencies whether or not the green band needs that spectrum or not. So exclusion zones alone, and sort of as a binary, are not going to be the answer, as they incur serious inefficiencies. And so ultimately, either the active users are not going to have good stake in using the spectrum, or the passive or military defense users are going to incur interference. And we don't want to have it either way. Then the question is, what can we do? And this issue just unfolds. And what I'm flashing here is a bunch of articles from the past couple of years that just underscore to the public coexistence issues, stemming from 6G and beyond, kind of stepping into remote sensing for climate prediction bands, to CBRS, interfering with garage door openers, 5G networks interfering with Pentagon's operations, or mega constellations interfering with radio telescopes. So in order to start solving these coexistence issues, we really should have a way to bring different stakeholders together to first talk about their capabilities, or maybe first talk about their pain points and trying to share so far. And then from there on, learning from these lessons and starting to ponder upon, okay, well, how do we even begin to coexist together? So there have been a couple of examples, most recently, of the scientific community coming together with active transmitting commercial technologies. This is an agreement that NSF facilitated between SpaceX or Starlink and the radio astronomy community, that is currently ongoing with the National Radio Astronomy Observatory, between them and Starlink anyways, to try and understand how much of the downlink in Starlink technologies is going to affect radio astronomy as far as the NGVLA is concerned. But it is hard. So we're basically trying to bring together commercial stakeholders who try to maximize profit, and their technologies are both transmit and receive, have really low sensitivity as far as other stakeholders are concerned. And they basically try to minimize the cost for consumer grade equipment so that they're marketable. Trying to put that together with the counterpart of the scientific users, whose goal is to maximize social good, and that is not necessarily something that can be measured directly or easily in terms of a profit. And technologies are often receive only. They're highly sensitive, multiple orders of magnitude more sensitive than anything meaningful for commercial broadband, and they're highly costly, specialized equipment. So bringing together stakeholders with different success measures, different capabilities, but with the same long-term objective of getting more spectrum to them so that they can do their job better. So if we can hold on to this thought of getting more spectrum for everyone as a unifying factor for bringing us together to speak, now what can we do in order to start efficiently unraveling, from that objective down into what actually needs to happen for us to begin coexisting? So the big question here is how to facilitate really mutual understanding, trust, as those different stakeholders come together, because trust, as we see in the past, has been infringed on, and that has created a big rift in our ability to communicate. And what experimentation needs to be designed in order to support spectrum coexistence across these very different stakeholders. So this is where this concept of national radio dynamic zone comes from. And these are really just some definitions or thoughts of what NRDZs might look like based on the community input. So we asked 10 researchers what it should be. You'll get 15 different answers, and that just signifies how challenging and important of a problem that is. But broadly, the consensus is that a national radio dynamic zone will be a system of systems. So there will be possibly individual smaller radio dynamic zones that are focusing on some specific coexistence scenarios that might come together under unified control for joint experimentation. It will require a very clear policy and enforcement principles in order to ensure that stakeholders will really be able to or willing to come together and efficiently make use of the spectrum. It will require access to new frequency bands for all users to be able to expand in what they currently can do and experiment and really gain benefit. It will require new and advanced spectrum monitoring in order to enable both science and wireless ecosystems. It will demand coordination across these very different spectrum communities, and sharing will be multidimensional. So we've kind of started from 3, time, frequency, and space, and as the various communities broaden their perspectives, I think we're at 7 dimensions now, thinking about geometry and geography and polarization and all of that. So how do we share across such a rich dimensional space is also a big challenge. Exceptional protection for those most sensitive users to not be interfered with, and incorporating both terrestrial as well as non-terrestrial communications as well. So, effectively the observation is that we need to depart from the current spectrum axis of I have spectrum, I have not spectrum, or spectrum is used or not used based on what's actively transmitted, into a more cohesive framework that promotes sharing and mutual awareness and trust. And if anyone is interested in what the initiative has produced so far, this is a website where we've been documenting all our outcomes, and I think I have this in my bio, but if anyone is interested or has questions, I'm happy to take it over email afterwards. So in terms of the vision that transpired from these 4 years worth of discussions so far, just in general, the National Radio Dynamic Zone will be a volume of spatial frequency time resource where we will be able to do experiments in a controlled manner, in a way that electromagnetic energy would not be departing or entering within the zone. And from end users' perspective, end users being all of us stakeholders that are looking to get more into more access to spectrum, the zone will be able to provide interference-free or interference-controlled access to spectrum up to the terahertz range. I see a question in the chat. Okay, not for me. And so essentially, the zone is conceptualized in terms of a set of physical components and functional components that have to come together in order to enable these testbed capabilities. In terms of physical components, effectively, we vision various experimenters and various incumbents on parts of the spectrum. Some incumbents might be managed, or in other words, willing to experiment for coexistence purposes, such as radio quiet zone users here in the United States within the radio astronomy community. Other incumbents might be unmanaged, such as a cellular provider who happen to be in the zone, and we have to be able to avoid them. And then there's various experimenters that might be those cutting edge active transmitting or passive technologies that are gonna wanna test their capabilities within the zone. This will be wrapped by various functional components, well, 3 functional components really, that will deal with design and enforcement of policies within the zone, that will deal with experiment management in order to ensure that various experimenters are going to come and gain maximum benefit from the zone while not interfering with other experiments. And the third component would be spectrum management that would effectively deal with measuring and managing how spectrum is allocated across the various experimenters. So in terms of beneficial outcomes from the zone, for the broadband wireless community, this can enable potentially access to the massive throughput and ubiquitous coverage requirements that the industry has been proposing in order to be able to test those ever large bandwidths and frequency ranges while coexisting with other spectrum users, or while being mindful of other spectrum users. In terms of radio astronomy, the hope is that as radio astronomy instruments continue to grow in their capabilities, a radio dynamic zone will be able to provide free of interference spectrum so that those instruments can be actually used to their full capacity. And what the zone can provide for that is the ability of everybody else to keep quiet for some nominal amount of time, so that interference-free observations can happen within the 20 gigahertz instantaneous bandwidths that the NGVLA is now projected with. Additionally, having a zone in which spectrum access can be managed with an outlook toward protection can help stimulate more investment in designing even more advanced instruments and having a guarantee that there will be enough spectrum for those instruments to be deployed on and for the sciences to happen. For remote sensing too, effectively guaranteeing allocations of spectrum for a certain amount of time without interference, so that they can perform observations onto Earth undisturbed by other emissions as well. Which leads me to a bunch of challenges in realizing this vision. So I mentioned sort of the three pillars in the radiodynamic zone design around spectrum policy, around experiment measurement, and around spectrum measurement. But in order to realize those three functional components, we have to walk quite the path. So currently, spectrum policy, as we saw, is really siloed, and policymakers are going to have to get out of this siloed way of viewing the radio spectrum and into a way that would, within the zone, be able to allow coexistence and the different stakeholders being able to spill over larger spectrum and then shrink back as other stakeholders expand. And so the thought here is, how do we enable this? Are we going to design the zone as a fully open spectrum access system, sort of the Wild West of where everybody is doing what they need to be doing, or is it going to be fully licensed, managed by some sort of entity that deals with the zone? So effectively, boiling down to how do you create this experimenter's paradise across the different stakeholders in order to maximize the availability of spectrum while minimizing the potential for harmful interference. Another key component of the policy framework that the zone is going to require stems around or revolves around enforcement. So how do we both allow this big spectrum experimentation while also ensuring that various stakeholders that come together within the zone are protected in a fair and efficient manner? So aspects or options that we've been pondering upon is, how do you even measure in order to enforce? And what do you enforce with? Fines, loss of access to the zone, reputation scores, so that figures into the next time you want to do an experiment. And it's really, as open as it sounds. The second key component that I introduced was around experiment management. So this too will have to be a core component of the zone, to where the various experimenters coming together will have to be allocated basically a volume of the zone in order to perform their experiments. And then the question then becomes, what is a volume of the zone? Are we going to kind of create a unit measure for the radiodynamic zone? And what is going to be the metric to that? And how will it sort of sit with this multidimensionality across time, frequency, space, and any other considerations that we may have arising from the capabilities of the technology? And then having created that unit, how do we use that in order to allocate it to the various stakeholders who are going to be experimenting within the zone? In terms of creating the physical environment to support experimentation, we have stakeholders with very different capabilities and very different price point to the equipment that they will be bringing. So we don't think that we will replicate the radio astronomy community's instrumentation just to have it in the zone. Maybe some of those zones are going to revolve around existing capabilities. So how do we ensure that those are protected is a key question here as well. And then finally, issues around spectrum monitoring are essential in ensuring that the spectrum is fairly enforced on, and the various experimenters are observed as they proceed to use the spectrum, and are verified that they really are only doing what they were authorized to do. So spectrum monitoring is challenging in of itself, and now we're looking to be able to monitor stakeholders that can support gigahertz, tens of gigahertz instantaneous bandwidths with very sensitive receiver technologies. So what is meaningful to be able to capture for those stakeholders and characterize as interference, and how much spectrum monitoring capability is necessary in terms of sensitivity, in terms of instantaneous bandwidths of the monitoring subsystem, in order to be able to efficiently enforce on those various stakeholders. What characterization of the measured spectrum is necessary? Is it just, there is interference or there is not? Or is there a need to perform more detailed characterization that goes into the, the specific technologies that might be interfering, and into aspects of localization and determining waveforms and determining the stakeholders that might be inflicting interference. So all of that creates issues and grand challenges around just how do we realize a monitoring system that can support coexistence across such vastly different stakeholders. So I want to pause here. That's as much, and sort of transition into a bit of our work on spectrum monitoring for mutual awareness and coexistence. But are there any questions around radiodynamic zones and their place in the universe as they stand? All right, so maybe
I might have a question. I'm not sure if this is maybe covered in the next section or not, but like in terms of enforcement, how do you see, like I saw loss of access. How do you see basically enforcing that somebody doesn't have access to a certain zone?
Right. Yeah. I mean, in terms of enforcement, that's effectively a two-step process. And no, I don't really have this in the next slides. So it's a good place to ask. So the first step would be really being able to monitor and gather relevant data for enforcement, analyze that in order to determine that there's really a rule broken in the first place. And then as a second step, and I think what you're interested in is what do you do? How do you punish, the one stakeholder who broke a policy or who broke a rule and infringed interference? So we don't really know. Some sort of ways that were mentioned throughout the discussion were that maybe there's going to be a reputation-based system where you enter with a certain amount of goodie points, and as you keep breaking rules, those are exhausted and ultimately you're banned from the system. And the other way around, if you're a good citizen, running your experiments without infringing interference, then maybe your brownie points are going to increase, and so you will have an even higher sort of priority in making use of the shared spectrum. But yeah, broadly, this might boil down sort of to an incentive system that needs to be developed. And coming back to how wildly different the incentives of various stakeholders are, that will be a fun exercise in and of itself, right? So your thoughts as are, I'll be comparing your thoughts as well.
Yeah, thank you. I'm sorry if I want to probe more into this, but like, how is this enforcement going to be backed legally? Is this like...
Right. effectively, the vision is that there will be some policy created for the radiodynamic zone, and this will have to be a mixed effort. I think if this is going to be a zone within the United States between the two federal arms that deal with spectrum regulation, the Federal Communications Commission that deals with the commercial use of the spectrum, and then the NTIA that deals with non-commercial use of the spectrum. But a lot of these stakeholders, particularly radio astronomy and remote sensing, their spectrum needs are at the international level. So I would absolutely envision that international bodies such as the ITU are going to have to come to the table in designing these policies as well. And then in terms of who enforces the policy, again, unclear. Some visions kind of point to that there will be slivers of the FCC and the NTIA that are going to be allocated explicitly to enforcing the policy, overseeing the policy for the national radiodynamic zones. Others think that there has to be a third body within the federal government established in order to deal specifically with that. Yeah, it's a mess.
Okay, thank you.
Thank you. I see one more. Oleg, your
Yes. Well, thanks a lot. Well, actually, I think it was Artyom. He almost asked my question already, but I will little bit add. So, but okay, effectively, are there any international legal policies of higher echelons that might prevent from such behavior? Because, okay, for instance, the situation with GLONASS that we do have now. Okay, we do have this situation, and so what? So are there any international mechanism, maybe it's on UN level, maybe on some other level, which effectively regulate violation of these policies on international level, not just on the US level? So that's the question.
Yeah, I mean, the involvement of the ITU has gone time and again, particularly from the Earth sensing community. I think if we're effectively trying to engage across the radio astronomy and the remote sensing community, we should be thinking globally, because these instruments, the radio astronomy instruments, are designed to operate from different locations across the globe, and they need to be protected by some sort of a unified policy. And so that policy should definitely come into play in how national radiodynamic zones are designed. And so with that, I think those respective communities are really pushing for the ITU's policies to be considered. But how exactly this is going to transpire, I can't tell. But in terms of creating a policy for this, it really should be harmonized to the geospatial footprint of the stakeholder. And so if the geospatial footprint of the stakeholder is beyond continental US, which majority of the stakeholders now that we're dealing with are, there should be definitely a multinational effort.
Okay, I see.
All right. I know. I wish policy was, was more advanced than it is.
Well, because effectively, technically, it means that if there is some policy in place, it's already something, even if there are no technical measures, so to say, to enforce these policies, but already it is something. Because otherwise, right now, it seems that nobody can do anything, like, for instance, with the GLONASS situation. So that was the question.
Right, exactly. Yeah, so I guess the idea here is to be able to characterize those issues in a more experimental way than the modeling based approach that was used with GLONASS, in order to know what the extent of harm is going to be before this thing is launched into space and there is no turning back, is ultimately the idea. How exactly this is going to transpire, right, still up for debate. But I think what's encouraging is that there is now a lot of awareness, both within policymakers as well as at least within the academic community, and I hope through policymakers, the industry is going to be roped efficiently into that as well, that we need to be looking more holistically and more practically in terms of what harm is being inflicted, and enforcing on that. And I guess the best we could come up with as a community is, let's have a big test bed and experiment with these stuff instead of only limiting ourselves to simulation and theoretical models, to see whether we really are going to cause the interference that, or not cause the interference that we're claiming to, and then move from there. All right, so 5 more minutes or no more minutes? Gaman, you're the...
Yeah, keep going, please.
Okay, so in the second part of this talk, I want to focus on some of the work in our lab that deals with spectrum measurement and spectrum analytics for coexistence and mutual awareness. All right, so the way we've been looking at the spectrum measurement ecosystem is as follows. So basically, it's established of a bunch of physical components, both some that we're targeting to measure, such as various transmitters, as well as physical components that are going to help us measure those target emitters. And the sensing front ends that we're considering are anywhere from a low-end $20 RTL SDR software-defined radio to tens of thousands of dollars high-end spectrum analyzers. Those will be collecting traces for the radio environment that would be then stored in some sort of back end for further processing and analysis. And on top of these physical components that measure the spectrum, there are a set of functional components and data flows. Oops. Some that deal with spectrum sensing, so driving the sensors to collect the data that is necessary for a particular analysis task. Spectrum awareness, and the way we define this is effectively given a broadband trace such as this with multiple transmitters being present in it, being able to characterize how many transmitters are there and what's their activity over time and frequency. And then as a secondary characterization task to that, we also conceive of transmitter tracking. So once you have this broad awareness of how many transmitters are there and what they're doing, zone in or hone in on individual transmitters in order to say more about what they are, including where they might be located, whether they're mobile or stationary, and what modulation might they be using. And all of that with the idea to be able to, in more detail, profile a particular transmitter for the purposes of enforcement or for the purposes of efficient coexistence. These will need to employ various data presentation techniques, either through visualization or through plugging into a system for coexistence, and ultimately would be supporting a plethora of spectrum applications, maybe supporting spectrum policy that departs from spectrum use unused and makes use of more longitudinal and detailed fine-grained view of spectrum occupancy. Might feed into spectrum sharing networks to support coexistence, might feed into enforcement in order to help an enforcer decide whether a device that is present is legitimately operating or not, and might feed into user privacy and security considerations as the spectrum is observed. So in terms of the functional components, this here to the left, the spectrum sensing component, is what produces data, and these to the right are the ones that consume data. However, what we've observed is essentially that there's a fundamental disconnect between our sensing between the requirements of analytics, or the sensing requirements of analytics, or in other words, the types of traces that spectrum awareness and transmitter tracking require, and what measurement capabilities we have right now. So to give more perspective, here's what the requirements for spectrum characterization or transmitter characterization have been so far. So effectively, we kind of need to know what we're looking for in order to be able to characterize it. Particularly, we need to know what's the bandwidth of the transmitter, what its operational frequency is, and what waveforms and supported modulations it has. So I kind of have to have one-to-one capability between the transmitter and the corresponding sensor as you go to measure that spectrum. However, spectrum sensing is not going to be as precise, or is not going to be aware of the various technologies that are occupying the spectrum. And so as a result, it cannot be as targeted as originally required. So we're looking at a wide target frequency band. So currently active technologies are mostly within the 30 megahertz to 6 gigahertz range, and of course spilling over. But even up to 6 gigahertz, that's quite a wide target bandwidth to be able to measure and characterize. And in addition to that, we have our sensing capabilities basically bound to low to mid-cost sensors whose instantaneous bandwidth for a USRP here on the right-hand side is up to 160 megahertz view on the spectrum instantaneously, whereas those really low-cost radios, they can support up to 3 megahertz instantaneously. And so because the target bandwidth is orders of magnitude higher than the instantaneous bandwidth of individual sensors, spectrum sensing will be sweep-based. So a sensor will be stepping through sequentially a wider band of interest and will be collecting intermittently traces in individual subbands. And then the goal of spectrum analytics will be to characterize transmitters, as we posed earlier, based on those partial, or sweep-based views of the spectrum. So with sweep-based sensing, sensor bandwidth may be smaller than that of the receiver. So the receiver, transmitter rather. So a transmitter might be captured only partially. A transmitter might be captured partially and along sideband noise, or it can be captured alongside other transmitters, depending on how our observation hits the spectrum. So as a result, we need to bridge this gap between sensor capabilities and what's required for analytics to work. And that's where my work at the UBNet lab and of my students have largely revolved around. So bridging this gap between spectrum sensing capabilities and our ability to characterize spectrum. So we've designed novel machine learning algorithms for spectrum measurement and analysis. We've created the first sort of middle layer that sits between sensors and the tasks that are going to use the data on top, and effectively characterizes the fidelity of spectrum data to support various analytics tasks. We've designed transfer models in order to be able to reduce the data requirement to efficiently train characterization models. And we've also dabbled with design of efficient data management methodologies in order to compress data without losing spectrum features. So I was planning in this talk to focus on some of our work on spectrum awareness and some other work that dabbles with transmitter characterization. But I want to pause again and see how are we doing in time, because this is going to be, I think, more than what was originally planned in here.
How much time do you need for this? I think we can. This is all very interesting. So.
Okay, so why don't I go? I can talk a little bit about spectrum awareness, our spectrum awareness work, and I'll stop there. And I'm happy to have a further discussion, or maybe if you all are interested, I'm happy to give a full-on talk that focuses more specifically on the spectrum awareness stuff that we've done. If that's a route that we want to take. But so one of our early works in spectrum awareness is something that we call TX minor. And so the goal of TX minor was effectively to depart from this view of spectrum occupancy as a percentage of time that a given frequency band was deemed to be actively occupied by a transmitter, and into a more detailed sort of view where individual transmitters can be characterized in terms of their count. So in terms of their count and in terms of their bandwidth and spatiotemporal capabilities as they occupy the spectrum. So really questions that we're looking to answer were how much spectrum is occupied, but also how good is the available spectrum for shared access in terms of how many transmitters are already using it and what opportunity they leave for secondary access. And these we thought were going to be important questions to answer in order to support both policy as well as spectrum sharing technology. So in terms of policy, to help regulators such as the Federal Communications Commission to open up additional spectrum by answering who's using the spectrum and how much bandwidth can be shared on a secondary basis. And also help interested parties measure and characterize spectrum and make the case that there's an opportunity to share. In terms of technologies or how such characterizations can inform technology, we were looking to quantify which bands are continuously available and which are periodically available, what spectrum sensing would work to support characterization, how accurate might geolocation databases be, how much interference might be caused to the primary user through secondary coexistence, and support enforcement on technologies that cause radio frequency interference by being able to characterize those interfering technologies. So the goal here is, given a wide frequency scan, determine a transmitter, all the transmitters that operate within it, along with their center frequencies, their bandwidths, whether they use TDMA or FTMA as an approach to access the spectrum, whether they're mobile, and their location. So the key insight behind this methodology is that measured signals, the distributions of measured signals really can tell us a lot about how the channel is occupied. And just to give intuition here, there's 3 examples. So the left-hand side is a piece of spectrum that is idle. And so it's the distribution of signal measured is, basically a normal distribution centered around some power level, around the noise floor of the sensor. In the middle is a piece of spectrum that is fully occupied, and we see a different picture here where the distribution now starts looking differently, and the mean grows depending on the level of the transmitter that is being measured. And then in a third situation, we have a piece of spectrum that is occupied by 2 transmitters side by side, and this creates a bimodal distribution. And again, the distribution capturing sort of the different type of activity that is occurring in the spectrum. So with this intuition, we thought it might be useful to be able to create a model to determine how many users are currently occupying the spectrum and base our characterization on that. So creating such a model, however, is challenging because RF signals are inherently quite noisy. They're oftentimes, well, for any practical reasons anyways, always affected by some multipath phenomenon, oftentimes following relay distributions in non-line of sight environments. The background noise we observe, though, follows a Gaussian distribution. And as a result, we thought that the measured power can be modeled as a mixture of multiple relay and one Gaussian distributions, where the relays would capture the various transmitters that we observe, whereas the Gaussian will capture the noise. And hey, I had an animation that worked. All right, just as I said that, the slides broke. So more specifically, the way we model the spectrum trace is effectively as a mixture of relay and Gaussian signals. This would be the mixture of signals. Individual components would be represented with weights for each of those components, depending on how much transmitter activity was captured. There would be some number of relay distributions, one effectively fitted for each transmitter, and one Gaussian distribution capturing the noise. This is unsupervised. We effectively implemented as an expectation maximization algorithm that increases the amount of transmitters that are being explored while evaluating the goodness of the fit. And so effectively, when the goodness of the fit is perceived to be maximized, we stopped the optimization, and that can tell us how many transmitters are there and help us then backtrack and characterize these transmitters as well. So more specifically, the way characterization worked is as follows. Given a spectrum measurement trace, such as one fairly clear example here on this picture, we would model that trace as a relay Gaussian mixture model. And that would produce, in this particular case, because we see one transmitter and one noise component, would produce two distributions, one capturing the noise and one capturing the transmitter. With these distributions, then we go on to calculate the posterior probability for each originally measured power spectrum density to be associated with each of the distributions. So if we take a power spectrum density measure over here, the association probability with the transmitter component would be non-zero, whereas the association probability with the noise component would be 0. And eventually, by calculating the posterior probabilities for all of the originally measured power spectrum densities, we get a much smoother version of the original signal, particularly, as far as each original power spectrum density values association with each of the components goes. And then we use those in order to characterize the bandwidth, the center frequency of the transmitter, and what the transmitter does over time by extracting signatures and employing these signatures for characterization. So this was evaluated through real-world measurements with what back in the day was the Microsoft Spectrum Observatory. So Microsoft had an effort to build an observatory with multiple distributed sensors that would continually measure the spectrum across the 6 gigahertz range and collect data to characterize activity. And so particularly, we were focusing on a couple of bands for which we could establish partial ground truth so that we know how well this unsupervised approach is doing. We used TV and FM bands. We had a controlled WiMAX transmitter on campus that we used to generate some activity and collect traces. We had some proprietary television white spaces, which was the very early incarnation of dynamic spectrum access, and some artificially mixed signals. And in terms of performance indicators here, we were evaluating accuracy of detecting occupancy in the spectrum, bandwidth detection, transmitter type, and transmitter count. So without getting into too much detail in the results, we were able to, for various popular technologies, detect properly the bandwidth that they were operating on. And we were able to also use this approach to characterize longitudinally spectrum traces and be able to create an RF inventory of spectrum use, particularly focusing on the number of transmitters that were expected and detected in a particular band and their types in terms of broadcast versus various more intermittent uses of the spectrum. And so effectively, what this was, one of the early works in ingesting data from multiple spatially distributed sensors and being able to employ an unsupervised approach on top of them that didn't know what's going on in the spectrum, but was able to characterize the number of transmitters and some basic properties of those transmitters. All right. So I want to stop here in interest of time. As I mentioned, I had prepared a little bit more to talk about modulation recognition, but that's going to take me another 10 minutes, which you may or may not have. But I want to leave with a couple of thoughts here. So we have a unique opportunity as multiple communities here to come together and try and educate each other and think about how we might effectively start sharing spectrum, not in order to give, but in order to receive more. And so this convergence, though, of increasingly different spectrum technologies is challenging. And unless we figure out what all the stakeholders need and how to support those needs objectively and transparently, we're going to continue kind of trying to hide in our own silos, and that would continue actually, limiting the amount of resource that any of the stakeholders is going to have, which in line or side by side with the increase of capabilities that we have is just really a pity. And what we really need is design of measurement informed capabilities for spectrum sharing. So continue to look into data, continue to look into how to collect data that is trustworthy for everyone, so that when I, as AT&T, come and tell you that I'm not going to interfere with you as remote sensing technology, you can really take my word for it or require any additional information. And continue to do that while ensuring that whatever next generation technologies we design are equitable for all the stakeholders and for any end user perspective as well. And this is, really has to consider sort of where we are today and what issues are we about to face. So today we're kind of at the level of, all right, we can maybe enable technologies to coexist as long as they have comparable sensitivity levels. And we, cut up the space with protection zones and make sure that they don't interfere with one another. But, what we need to be able to, immediately deal with is mutual awareness in the face of interference. So scratch exclusion zones and be able to still be mutually aware of the presence of protected devices, even though somebody else might be operating in the spectrum. And start doing that with a mix of terrestrial and non-terrestrial technologies. And issues that are imminently coming is with technologies coexisting across vastly different sensitivity levels. And this would require going back to the table and designing measurement instruments that can help measurement and characterization with high sensitivity in mind. Coexistence, where some of the stakeholders are passive, so they don't really show up as using the spectrum, but they really are using it, and others are active. So how do we enable mutual awareness with passive and active users in the picture? And how do we enable mutual awareness with such different sensitivity levels, where some of the stakeholders are earthbound, where others are in space? So I'll stop here. Thank you very much for hosting me, and I'm happy to take any more questions.
Thank you very much, Mariya. This was very, very interesting, and I think food for thought for years to come, and then for action, of course. Are there any questions or comments?
Yes, I don't know how we proceed with the questions. Can we just raise our hands? Well, now I spoke.
Yeah, please. Go ahead.
So first of all, thank you very much. That was very interesting, very supervisory. I think it's needed. And speaking of supervisory, I was wondering, Mariya, concerning the manifested cases of interference, do we actually, do you have data for that? I mean, why I'm asking this is because at least the industry, because it's vital for the industry that this is, if it occurs at all, it's limited. The industry makes sure that the crosstalk between different stakeholders is negligible. But do we actually have a data that shows us how often this happens, how sensitive it is? And before you answer, sorry, I think we should keep in mind that radio astronomy, which is my background, so don't misunderstand me, is a very peculiar case. First of all, if not for anything else, for the extremely high level of sensitivities that the involved apparatus has. So I do not think it's a very representative test bed, if you like, whether radio astronomical instrumentation is influenced or not, because it's meant to be very sensitive, because the signal that it's after is extremely marginal. But for at least for the rest of the story, do we have data to tell how often such serious problems occur? Because the industry does take measures against those.
Right. Yeah, that is an excellent question. So the short story is, unless, well, the short story is no. I don't think we have data. So there is a big push in opening up data sets in order to be able to, particularly data sets where with multiple technologies coexisting, in order to be able to start understanding how those are going to look together. However, those are broadly, just some snippets of, and oftentimes of emulated or in-lab produced data that can help researchers such as myself, start to design methodologies to characterize spectrum traces. But I think the data that you're asking for is, do we have actually collected longitudinal data that we can then go back and analyze and see how much the issue of interference is, or how prominent the issue of interference
Or
is.
how often it has hindered our business,
how-
whether that's research or whether it's, yeah.
Exactly. So no, but I think what I found encouraging along these lines is, so for example, what the remote sensing community does, and I think to a large extent the radio astronomy community does, is the degree to which they're now capable of dealing with interference is basically excision. So they throw away a bunch of their traces that are polluted by interference and they move on. So, and I think those stakeholders just inherently don't have the resources to deal with that data, right? They are funded to continue evolving the highly sensitive instruments and to continue doing their sciences on the pieces of the data that are quiet so that they can, discover whatever phenomenon the science is after. And radio interference is this terrible thing, but we really don't have the resources, or haven't had the resources so far, to characterize it. So what I'm really interested in is looking in the garbage that's being produced by radio astronomy and remote sensing, because this can be very insightful precisely along these lines, right? Let's start, funding effort to characterize the level and severeness of interference. And then this has a lot of implications. It has implications on, okay, how big the problem is. We can quantify it now. But it has also implications on what is the level of sensitivity that we need to be designing with in order to be able to catch that problem proactively. Or so in other words, if I was to create this 3D or 7D measurement substrate within the natural radio dynamic zone that is going to continuously check whether radio interference is happening. If I'm able to look at the garbage that is being produced now through radio interference traces, tomorrow I might be able to answer what the sensitivity of those third-party spectrum sensors will be in order to efficiently be able to catch and enforce on interference. The National Radio Astronomy Observatory and one more observatory along the West Coast are spearheading efforts to create sort of an auxiliary spectrum sensing system that is just going to be basically, and I can point you to articles. So Chris Dupree, who I flashed at the beginning of my talk, is overseeing this effort. So they basically have a sensor, a set of sensors that they're building that are going to sit within the observatory and just continually measure a wide frequency range with that idea precisely, to be able to catch and characterize activity that is not supposed to be happening within the zone.
That may be the Owens Valley Observatory.
Gregoria, se me escucha el micrófono. Si puedes.
Sorry.
I didn't get the comment, but yes, I mean, there is definitely an outlook, and I think in the short run, we will be able to produce some data as a community, or I have hope that we'll be able to data.
The reason why I'm asking is if I can take one more minute, unless somebody else wants to make another question. It was not my question was very specific, is because I wanted to have a quantification of the magnitude of the problem, obviously, right?
Yes.
And why? Because I have the suspicion it's an opinion. It is not an educated opinion. It's just a feel. a gut feeling, if you like, that the problem is not as severe. On the one hand, the industry knows how to coordinate itself because they pay, so somehow they sort it out. And the scientific community, which in your talk has been focusing on radio astronomy, which is not the only sector, however. So there's also transmitting, as a matter of fact, scientific community, the radar community, for example. You know that better than me. This is I think it should be seen with a special weight that it deserves. And that is, again, on the sensitivity level, which is very, very different. I've been following your talk extremely interesting because I think it's very, very interesting. And thank you very much for that. The coexistence, the term coexistence and the term dynamic may mean many things. So just to give you a feeling, in the telecommunication industry, for example, which I'm currently probably a little bit more represent or observing like, for example, has been also examining the dynamic sharing of a spectrum, which is when you do not need the spectrum, I can use exactly the same band. And this is one scenario of coexistence. Another scenario of coexistence, we can simultaneously in time use exactly the same band of the spectrum as far as we are far apart, which is pretty much along the quiet zones that you are discussing. So I can give you a real example. These days, we are discussing with one of the people who follow this discussion, I hope, Dr. Winkel, about the coexistence of IMT, so mobile telecommunication networks, and radio observatories for a specific band, which is, by the way, non-protected. And I deliberately bring up this example because it touches on two important things. The one is the coexistence, and the other is what you said, the trust. So although the band is not protected for the radio astronomical community, Deutsche Telekom has always been very willing and ready to pay the bill, whatever that means, to protect it, even though it's operating in a non-existent, in a non-protected area. And this is done on the basis of trust. So trust, I think, is something that people can actually build on and probably should build on. On the other hand, we are discussing, for example, among the different scenario, the coexistence in time and space, or in space, as long as the time is actually controlled. So we discuss scenario, for example, if we could have a warning system that there is a very critical observation that is taking place, then the mobile stations can go to low power or actually can probably tilt to another direction so that they avoid directly irradiating the observatory and all sorts of things. So I think that everyone in the audience today would need another extra hour to discuss with you their concerns, like I do now. I just was lucky one to raise my hand first, but there is so many different parameters
Yes, exactly. And I mean, the whole idea with the testbed, with this national radio dynamic zone, is that, okay, yeah, these are all the viable paths moving forward in order to share. Let's use a playground to convince ourselves that this is actually going to work, to the best interest of everybody involved, before we start investing into, building this and deploying it globally.
That's exactly the point I'm trying to reach. That I think we should pick up on this and have follow-up discussions and get an even deeper understanding of what are the problematic scenarios of each one of us, of each organization that we represent or that we are interested in, and so that we can build an educated opinion on the others' problem as well.
Exactly. No, I love that, and that's really what we're driving towards. So,
and the very, very last point, if I may make, and that will be really short, the endeavor that you have undertaken with your team to build up models for the RFI, I think that's really a very interesting subject. Maybe, if not already, maybe you can consider also including, since you do that as far as I understood, you use machine learning, which is a multi-parameter problem tool. You can also include probably the spatial dimension, which from your presentation I understand is not included.
No,
because
definitely something of interest. Yes.
Yeah, but this actually this creates a holistic view to the problem, because the problem lives not only in frequency and time, but also in space. And in that case, all these three parameters should be accounted for. And
Right. Yeah,
So-
we're just starting to double with a multi-vantage characterization. So speaking to the choir, but yeah, I'd love to talk about this more. Thanks.
All right, maybe one last question because we went a little bit long, if there's any. I have a very brief question. Are you aware of any similar initiatives that are being considered or taking place in Europe or elsewhere on a, you know, large scale?
Yeah, I have not followed closely. I think there is an interest in Ofcom, which, as I understand, is the UK regulator, commercial side regulator, in facilitating a conversation with the radio astronomy community. So I think there's a thought process moving forward in Europe as well, but I have not followed it closely, so I cannot tell you quite what's going on. But that's where I would start if I was to try and learn more.
Okay.
may I make a last
Great.
comment, if I may?
Yes, sure.
So now this is going to be the radio astronomer, me talking, Maria. So you said a few times that the radio astronomical community expands or changes its interest in different parts of the spectrum depending on their capabilities. It's good to keep in mind that the radio astronomy is also modifying the part of the spectrum that is utilizing depending on the science which is hot at each time. So when I was doing my PhD, it was significantly different from what it was. And the limitations which are put to the radio astronomical approaches from physical factors, such as the transparency of the troposphere, the transparency of the ionosphere, etc., etc. So, for example, before the mid 2010s, that the Warlofer was being developed, or the SK was not there yet, the tendency was towards higher frequencies. Now there is a rejuvenation of the interest in the lower frequencies, etc. So I think this is also something to be kept in mind, because it wouldn't be a surprise, at least not to me, if there was an erratic jump of the interest from part to part. Not that this is important, but just for completeness of the picture.
Right. I mean, that's a very good point. I mean, we understand each other in terms of capabilities of the instruments, but then what sits on top of these instruments, I think it's still quite nebulous across communities. And what application you use those instruments. Absolutely.
I mean, around 2000, 2005, for example, the radio astronomical community had a jump in the interest around 30 gigahertz, and that was because the observational cosmology was developed, and that's because this is where the peak of the CMB and the minimum of the of the galactic transmission actually has a dip. So it was a sweet spot for doing such observations, and that could have faded away because the interest was shifted. So it's not as regular as, for example, the telecommunication industry, which approaches the problem differently.
And I should say that this is definitely a dimension that this testbed is considering. So, effectively the radio astronomy observations being able to report where they're actually measuring right now, so that it's not a blanket of you should not interfere with any of our capabilities. It's really a blanket of we should not interfere with any of our active observations right now, with the understanding that these observations can shift across quite a wide band, and the zone should be able to accommodate for that by reallocating other users to other spectrum.
Okay, great. So thank you very much. This was extremely interesting, and I hope that we will stay in touch and
let's hope
start future conversations.
Are we getting the video and the presentation so that we can absorb it offline a little bit better?
I'm happy to share the presentation.
That's good.
All right.
That would be wonderful.
Great.
Okay, so thank you all very much, and thank you, Mariya, for this very, very interesting presentation.
Yes, thank you so much for the invitation. Bye.
Thank you.
Bye, everyone.
Talk to you soon. Bye bye.